Okay, let's go. So this is my great pleasure to welcome Jan Zeman for this afternoon session, who is going to talk about polynomial matrix inequalities and the application in structural optimization. So please, Jan, go ahead.
Thank you very much for very kind introduction. So in the first place, I would very much like to thank the organizers for inviting me here. And I hope that they and you as the audience will not regret that afterwards. So as announced initially, my talk splits in two parts. In the first part, I will be talking about some industrial application, but here I can actually offer only linear matrix inequalities application. And then I will show some refinement of the previous result. But now I will really go to the subject of this very workshop. And I will introduce each part separately because the work was done by two distinct group of people. Well, in the first part in particular, I'll try to show you some results we obtained in collaboration with Compotech company. I will speak about that, why they were interested in collaborating with us. And it's actually related to composite cubes and the way how to reinforce them using some techniques of semi-definite programming. Most of the credit, of course, goes with Marek Tiburec, who is a PhD student working with me and my colleague Maciej Lepsch. As you will see, there were some experimental part also involved. So this is what these two colleagues of mine took care of. And again, this was done in collaboration with industrial partner. So, well, if you can read that, well, the company we were working with is working with carbon composite components. So I will first try to explain why they are interested in that and actually why they were able to turn it to some serious business. So this is best seen by comparing mechanical performance of this graphite fiber, which is the basic building block of that material, with conventional construction steel. And I will try to do the comparison in terms of something which is called tensile modulus or modulus of elasticity, which is actually tells you how difficult it is to deform a product made of those. Then there is strength. So this is something which tells you how difficult it is to break that. And then density, which is normally used for. So you can see that this composite-based material actually has similar density to steel. But in terms of other mechanical parameters, it highly exceeds conventional steel. So in fact, its modulus of elasticity is about 4 times higher. And in terms of strength, it is actually better by more than order of magnitude. So as a result, actually, the company is able to produce lightweight structures out of that, which perform significantly better than the one made of conventional metals. Well, of course, there is no free lunch at all. So because these structures are extremely lightweight and hence they are thin-walled, they are also prone to some elastic instabilities. And this is perhaps best seen in this simple cartoon, which shows a simulation regarding to some vibrational characteristics of a sample made of this particular material.
Sorry to interrupt. Sorry to interrupt, but we don't see the slides. We just see the initial slide. Okay, now we can see number 4.
Oh, sorry. So is it better now, Michal?
Yeah, now I can see number 4.
Oh, sorry. I really tested it in the morning.
So for me, there was no issue. I was seeing the slides one after one.
Oh, sorry.
Okay.
It was my computer. Oh, sorry for that.
Maybe.
It's okay, but of course, feel free to interrupt me at any moment. Yeah, so what I try to show here on this particular slide are so-called modes of vibrations. So these are particular frequencies at which if you excite a structure, it is really willing to vibrate with minimum amount of external excitation. And if you have a look closer to it, actually, there are 2 pronounced frequencies in which the structure is willing to vibrate. The second one is the one for which the material is designed for. So this is when you take a advantage of that particular material system. But there is first fundamental frequency, which is associated with changing the shape of cross-section. And the ratio of these three is typically 3. And because this frequency, the smallest fundamental frequency, it sets the operational frequency at which the product can work, this is particularly critical for machine components. And this is a part of things the company is interested in, in developing. So, of course, they are aware of this problem and they have some ready solution. So the existing approach they adopted is based on using some high density foam, which they insert into the interior of the structure, which is done manually. So it is really time and cost intensive. And moreover, there is no clear way how to select the particular parameters of that foam structure. So, yeah.
So you represent your tube as the square section. I mean, is it useful or this is a very side question?
No, this is okay. Yeah, so they produce tubes which have this particular cross section, and how I will represent that, I have dedicated slides to that. But anyway, thank you. So what was their goal was that they wanted to take the existing approach. Take this high density foam and actually replace it with something which is high porosity, so something which is light. They would like to replace this manual production by something which is fully automated, and they of course would like to do it in a way that its reinforcement of the interior is optimal in certain sense. And the answer we were eventually able to provide rests on 3 pillars, which are mostly well known here to the people in the audience. The first one is semi-definite programming, so you can actually do that with linear matrix inequalities if you adapt some basic principles of topology optimization of trusses. And there is a bit on how to produce this using nowadays pretty standard additive manufacturing procedures. And this is the sample on which we agreed on that we will test the method, starting from computation up to actually validation of the manufactured sample. So this is basically what I would like to share you with in the first part of the presentation. So to reach the goal, I will first spend some slides on introducing the background, namely speaking about how we model the individual parts of the structure. Then I will go to optimization problems, so how to take this industrial assignment and convert it to something we can solve to global optimality. Then I will briefly touch manufacturing, verification, and validation steps. And then I will try to sum things up. Okay, so first to the modeling. So this is how we will actually represent the structure and what is the final design. So the structure consists of 3 basic parts. The first one is the outer composite beam, which has this square cross-sectional shape and, well, it's thin-walled structure. Then there will be a certain layer which will be 3D printed. This is something which we call casing, and it's introduced mostly for manufacturing purposes. And then there is this internal structure, which we again 3D print from some commonly available plastic. What is interesting is to observe the ratio between elastic properties of this composite beam. So this is this high-tech application. Well, if you recall still the numbers, so there is a knockdown factor of 4 approximately. This is because these fibers are embedded in much of the matrix, but still this is something which is comparable to steel. And the properties offered by standard plastics used in 3-dimensional printing are by 2 orders of magnitude smaller. And we will develop a finite element model, meaning that we will represent the structure by means of matrices. Well, the 2D part of the structure, so this and that part will be modeled as shells, and the interior of the structure will be modeled by 1D truss element. So this will be our modeling strategy, which is rather well established in my field. So just to, yeah, sure.
So what is the role of the inner material?
So the role of the inner material is to increase the fundamental vibration eigenfrequency. So this is when I will aim. So I would like actually to make this first value and to increase it above some defined threshold by designing the interior of that tube. Yeah, so sorry for not explaining that properly. Okay, so now how we model the behavior of the structure. So that the two outer layers, they are modeled by something which is called shell element. So this is a dimensionally reduced model, which actually reduces the structure to the surface. So this is how it works. For the further discussion, what we will need is that there are two terms which build the model for us. The first one is corresponding to stiffness. So this is something which tells you how difficult it is to bend your piece of material. And then there is also something called mass matrix, which tells you what are the inertial properties of that particle one element. And what is also important is that we need to have support of anisotropic material because that fiber structure mechanically behaves differently in different directions. As for the reinforcing structure, we will use trusses as the building blocks. They hence are also characterized by stiffness and mass matrices with the same meaning. And what is essential about trusses is that these are materials which can only transmit or deform in actual direction. So in the direction of center line here. So if you try it with any materials, these are super stiff in the direction, and this is what makes them so mechanically advantageous. So now a bit more about the matrices we use that. So for the shell model, the matrix which describes the relevant behavior is of dimensions 20 by 20. This is because the element consists or is defined by 4 nodes, and in each node we have 5 unknowns, 3 translational and 2 rotational degrees of freedom. And by physical considerations, this is positive semi-definite matrix, so it is rank efficient. The mass matrix, on the other hand, is positive definite. Same thing holds for the truss element, with the exception that this elementary matrix is smaller, is 6 by 6, because we have 3 degrees of freedom to describe the movement of this node and that node. And well, this is the particular way how we build these two matrices. The reason why I presented it here is that this is something well established, so this is reliable model. Okay, so this is the first part, which actually, specifies what is happening on what part of the structure to which we discretize the problem. What we would like to solve is this following generalized eigenvalue problem. So we are taking the stiffness matrix of the whole structure, from which we subtract some constant we search for, multiplied by mass matrix, and we seek for which values of this parameter the matrix becomes singular, and this is then what tells us what are the frequencies which are potentially dangerous for the structures. These matrices, K and M, these are matrices which are obtained by assembly or contribution from the matrices on the element level. So if you have some prior knowledge in finite element method, for instance, this is exactly the procedure which is used here. By again, some physical consideration, the resulting matrices are positive definite, so they are not rank deficient and still symmetric, and they are sparse, by the way, how the model is built. Well, this is certainly not something we would like to work on. What we actually will need is some variational characterization of the fundamental eigenvalue. So this fundamental eigenvalue can be found by minimizing this expression, which is called the Rayleigh quotient, which is obtained by taking some energy which is stored in the system while vibrating in an elastic manner, and we normalize it by inertia energy. And by minimizing this ratio, we get the first fundamental eigenfrequency. So eventually, by straightforward argument, you can see that this is equivalent to that equation, which eventually tells us that this must be positive semi-definite matrix. So this is equivalent characterization of that particular system, of that particular physical consideration. Moreover, as shown in this 2007 paper, if we would like to bound this fundamental eigenfrequency from below by this F over bar, it can be done precisely in the same manner, except for the fact that this first fundamental eigenfrequency is replaced by this given lower bound. So, I mean, what we were initially requested can be rewritten as this matrix in form. Okay, so this is what we need from physics or mechanics, if you wish. And final thing, and yeah, well, I really feel inappropriate to say it here, but we would also like to pose everything as a semi-definite program. So we would like to take the assignment and formulate it as a minimization of a linear function over, well, the conus positive semi-definite matrices. And what is important is that what is contained here in the constraint depends linearly on X, hence we have LMI type of problem. Okay, so these are the ingredients. As for the specification of this optimization problem, so what we do is that we follow something which in the relative field, in the appropriate field is called ground structure approach, which is fancy name for saying that, we pick some shape with which we will just fill the interior of the structure. And this particular shape defines all possible structures we will consider in the optimization. You can see that there are certain vertices here of this shape. This then defines where the unknowns of the mechanical problem will live. And the optimization parameters are cross-section areas of these individual links. So by particular discretization, we have, we have the space on which our decision variable live. All of them, these cross-sectional areas, by definition, there must be no negative, and there is some upper bound on them as well by manufacturing constraints. So this is one thing. What is even more important is that because of very particle modeling decision we made, the stiffness matrix and the mass matrix depend on the optimization variables in very simple way. So there is some constant or design independent part which corresponds to this outer layer. And then we have contribution of this internal reinforcement structure. And well, the matrices which enter there, they'll scale linearly with cross-section area, or these, yeah. So these paths here, they actually correspond to stiffness matrices of an element with the cross-section area equal to 1 dimensional. So this is important, and this is what allows us to use the semi-definite programming approach. So with that said, I can now formulate the optimization problem. So, well, the basic assignment we were about to solve is written here. So we seek for the minimum volume of the reinforcement. These A's are cross-section areas, which we multiply by length of individual connections. So in total, this gives the volume. And this is subjected to this constraint on the fundamental eigenvalue. So when we were discussing further whether this is enough or not, we were also warned by the industrial partner that this is not it, that there is additional constraint active, which is actually related to the fact how the structure is produced. So this is what the scheme tries to summarize. So we have this some metal part here, which is again a thin wall structures, which will then serve for manufacturing purposes. Then we have these links, they just highlight this ground structure, which is discretizing the interior. And during the production process, the sample is subjected to pressure from four sides. And for, yeah, sorry.
You have the elements, the fillings, presented then by Q, with lots of trusses inside.
Yeah, precisely. Yeah.
And so you're going to add this cube one. I mean,
Yeah. So you basically take them. Yeah, and there are specific parameters. These are selected in a way that you can completely fill the interior by repeating this primitive volume or this primitive shape. And these trusses, there are really segments, and what we are searching for is the area in perpendicular direction. So, no, that's fine. Thank you. So that additional constraint I will consider is shown here graphically, meaning that during the production process, actually the tube is compressed for full size. This is exactly how this is produced, and this is the pressing pressure. And to have really something which is applicable in target applications, you must ensure that the deformation which will be induced by this load will actually remain under some limit. And the way how the structure deforms is defined by this linear equation. So, you know, it has actually the similar structure as this part. It is a bit different because the structure is supported in slightly different manner, but if you are interested in getting the unknowns, you need to solve this linear system. Okay, which is unlike the first two considerations, is well inconvenient for linear matrix inequalities because it does not have the right form. So again, after some additional discussions, we actually found out that while this limit value is not something which is given as some ground truth, this is something estimated by rule of thumb, as usual in engineering. Then we were allowed to change this maximum displacement of the structure or the deformation by something more convenient for us, which is called compliance, which is again widely used in structural optimization. So if you have your structure, you exert a certain force on that, you measure the displacement which the force travels, and you compute the work done by the force on that displacement. This is what is called compliance, and this is what you usually try to minimize. So in this particular case, it will then provide some upper bound on the compliance. And there is some way how to take this U limit given by industrial partner and convert it to the upper bound on compliance. And the reason why we are so interested in that again, it's well known in optimization community that this particular constraint can be represented as linear matrix inequality. So this pretty much closes the loop from the point of modeling, because we took this original problem and we formulated it as linear matrix inequality. To accelerate the solution, there is one additional bit I wanted to comment on. What is specific about our particular problem is that these matrices we are working with, they always contain some design independent parts of the model, which are associated with the exterior, and these parts are significant. So if you use standard Schur complement type of manipulations, you can actually reduce these constraints to the form in which they contain only design-dependent parts, while this Schur complement is dense, but you know, it reduces the size considerably. And the same thing can be done also for the fundamental eigenvalue inequality. So this is another numerical trick how to speed up the solution of it. So then here are the results of the optimization. So as an input, we were given the fundamental eigenfrequency limit of 300 Hertz, and the deformation of the structure must not exceed 1.5 millimeter because these are high precision applications. So the particular discretization we used employed this number of building blocks I have shown before, which gives us something like 10,000 of decision variables, which we solved using MOSEC at some distributed cloud service called Metacentrum at Czech Republic. And well, this just illustrates what is the typical size of inequalities we encounter, what is the typical time and memory requirements, and what is the added value of eliminating this design-dependent part. And well, this is a 3D rendering of how the optimal reinforcement looks like. So I do not know whether this is really visible, but actually it has some specific shapes which are oriented orthogonal to the axis of the beam. And there was substantially more connections. These are just left out from the optimization. So there are at the ends of the structure, but not in inside. Okay, yeah.
Looking at the runtime, see around 20 to 6 hours. How long do you actually is acceptable waiting time for this optimization? Because as I understand, you do it and then you have your design and then it's manufactured.
Yeah, precisely. So as I will show, this manufacturing process is not something you will do in a blink of an eye. So I mean, for a company, this was acceptable, but certainly there are ways how to accelerate this.
So it's more like how quickly they can design.
Yeah, precisely. So I mean, for them, you know, waiting for 6 hours is certainly okay, because then their workers will spend some time on producing the sample. So this is no issue for that. You're welcome. So this gives us the design we would like to manufacture. So this is how we proceeded with the manufacturing. So we took the design because of this one-dimensional character of the structure. We segmented it in orthogonal directions. Then we did some post-processing on the design such that we will we will respect the manufacturing constraints and also some instability of these beams. So this is how eventually a typical modules looks like. So this is what we have. Then these were in parallel printed in conventional 3D printer. They have this space inside, which allows them to be inserted on the steel profile. And then eventually the company, you know, executed their standard technology, meaning that they introduced this additional layer. And if one then inspects the manufactured sample, so this is what you see in the interior, and to our surprise, it seemed that everything worked okay. These parts were not damaged during manufacturing, and you know, somehow the structure survived all the steps of the manufacturing process. So now, yeah.
Sorry, maybe at the picture before.
Yes.
Could you explain in those modules what the things are that you're optimizing?
Yeah, so what we were optimizing were cross-section areas of these connections, so of these tiny bars. And what we started with is the assumption that there is some, you know, the set of all possible bars which can be encountered in the structure is defined by this elementary cell, which is repeated. So there were significantly more connections than you get in the optimal design. And this is, you know, the whole business of topology optimization, to take these unwanted parts and take them away.
And in one slide, it said that there are as those 47 times 4 times 4.
Yeah. So what you mean? So this is, sorry, this is the size of matrix inequalities we encountered in the computation. So this is computation. So what I just wanted to say, that at least to my standard, this is large scale problem, but you can perhaps educate me that this is not. But it took some time, so the solution is not for free. So sorry, I didn't discuss that part, but I'm computation guy, or I'm also. Okay, so now we have, you know, the manufactured design. So what we also did was to check our results, which were done in in-house MATLAB codes, against some industrial standard. So this is what we get if we take the structure, insert it into standard commercial software and run the analysis. So this is the first fundamental eigenfrequency. You can see that the shape in which the structure vibrates, it's not exactly what we wanted to see, but it's closer to where the properties of the material are optimally used. If you still recall what was the target value or the lower bound for 300, but this was, you know, this value does not come from the fact, or this discrepancy that something was wrong in the optimization. Actually, we found out by in situ inspection that the thickness of the structure which were produced by a company is not the one we used in design. So this is major source of this discrepancy. But still, if you do the calculation without this internal reinforcement, you double almost the fundamental eigenfrequency by, introducing this low amount of not high performance material. And finally, what we also did was some validation step. So we executed something which is called experimental model analysis. I will not pretend that I'm expert in that, but the method works in a way that you plot some grid on your structure, then you hit it in one place, you record a signal from all the other, and via some Fourier analysis, you actually are able to extract what are the modes in which structure vibrates by just looking at the spectrum. And this is what we get from measurement. This is what we get from simulations. So you can see that the numbers here, they differ up to 10%, which according to industrial partner, this is acceptable. Okay, so this brings me to conclusion of the part 1. So what I wanted to show in the first part, that you can really take some high performance product made of, one of the most performant materials available on the market, and you can increase its performance, mechanical performance, significantly by using some, hobby level facilities. This is something you can purchase for 1,000 euros. But of course, you must do the design properly, and this is what semi-definite programming can do. So regarding the initial assignment, so we were able to replace this high density foam by high porosity truss structure. We could do that because we replaced the design by intuition by globally optimal solution. And this manual production is ready for Industry 4.0 type of automation because everything is defined in the modular manner. And for instance, these are the parts of the structure which can be manipulated by robots. So, I mean, if my informations are correct, the company is working towards that solution, but they were not completely open in sharing that knowledge with us. At this place, I would like to thank the grant agency for funding the computational part of this research. And actually, this was also appreciated by industry. So in 2019, before COVID, we were actually nominated with this product for the innovation prize of this GEC World Exhibition, which according to our partners is the largest exhibition of composite manufacturers. So we were not selected, but the nomination at least was done. So that's it for the first part. And are there any questions? Yeah.
Any slides back? No. Maybe 1 or 2 slides more back. I was just wondering about one more. It looks like there are many. It looks very, very symmetric, right?
Yeah.
This is something you already observed in the STP, or something that turns out to be true afterwards?
So sorry, I didn't comment on that properly, but I mean, the way how the problem is formulated, it's highly symmetric. So I mean, it's not perfectly symmetric. No, sorry. The way how this is formulated, it has some internal symmetry, and the solver discovers that. So we could have used this symmetry in constructing the solution. That is correct.
But it's not so big. Like class, the next bit of it is
Then this is something I will need more time to I cannot see it. Sorry. Can you give me a closer pointer? So this one, that
Missing
one.
two, so they- yeah, you're missing two legs. Just this leg and this leg too. I mean, you see this is not good.
Oh, correct. Yeah. So
This, no, this.
so it might be some. Yeah. So that's good observation. I cannot comment on that, but I mean the assignment is almost symmetric. So there is some slight asymmetry in the way how the structure is supported in operational mode. But well, my intention, so my impression was that this was resulting in manufacturing. So the result should be seen. So thanks you for that.
And the first box,
Mm-hmm.
you have a kind of rotation.
Yeah. So this is what I can explain. This is related to the fact that at the end the structure would like to undergo some torsion. So there is indeed some rotational mode, and this is something which just reinforces the structure against that. So there is some mechanical exchange.
But this depends on how the force is.
Yeah. But in this case, everything is uniform because there are two cases we consider. The first one is the one in which the structure is subjected to this pressure from all sides. And the second one is in which the structure vibrates. So the forces are distributed. And for the vibration, there are this inertia and elastic forces, and they are also distributed. So there is no local type of effect. So this is for this particle loading. Okay, so then I have still 20 minutes to go. So I would like to proceed to the second part. Yeah, sorry, and some bit of advertisement. So if for some reason you are interested in hearing more, well, it was published in this journal about which you have never heard of, and there's also archive preprint if you wish. Okay, so sorry. So this brings me to the second part of my talk, to which again Marek was the main contributor. But we were also joined by our two mathematical colleagues, Martin Kruji, which is also affiliated to our faculty, but namely by Didier and Rion, which you all know here. And well, it is in a sense logical follow-up from of the previous part of the talk, because the thing for which we optimized was the task, so the structure which can either extend or compress. But there are certainly easier way how to deform the structure. So we can bend it, for instance, in this manner, which in the previous example, this was the role which was played by this outer envelope. But what to do also to design structures for these effects, right? So this is the question I would like to address in part 2. And in order to achieve that, I unfortunately have to bother you with some details on how exactly the structure of this matrix looks like. What I forgot to comment on that for simplicity, we will exclude dynamic effects. We will just, concentrate purely on static case in which the structure is deformed. This is described by system of linear equations. So the most simple setting we can possibly think of it. So once we have this additional look on stiffness matrix, especially for this audience, it becomes obvious that actually there is some polynomial extension of the original setup, which is treatable by lesser hierarchy. Sorry. And I will walk you through individual steps, what we had to do in order to make the problem accessible to currently available techniques. Then I will show some examples and sum up things at the end. Okay, so as I told previously, we will be now working in the most simple setting, meaning that we will concentrate now on two-dimensional structures. So these are structures which just lie in plane. And as already announced, you can take one element of your structure and you can either extend it or you can bend it. And this is well reflected in the structure of the stiffness matrix. So in general case, it depends on two quantities. One is the cross-section area. So this is the area you can measure here for this, for instance, for this bar. And this occurs at these 4 points of the entries of the matrix. And the fact we actually exploited a lot is that this part of the matrix scales linearly with the decision variable EA. The remaining parts are constants, which are related to material from which the structure is made of, or the length of the structure. So this is of knowledge. In order to describe this bending effect, we have additional terms which contain this new variable for IE. It's called second moment of area. And it is, again, something which characterizes the cross-section. So this is a number which tells you that actually, if I, again, take this ruler, it is much easier to bend it around this axis than to do it in the perpendicular one. So this is something like moment of inertia. I do not know how to explain it better. The fact that this is called second moment of area suggests that this is no restrictive at all to assume that this can be polynomial function of the area, and for many cases of practical interest, this is indeed the case. Okay, so we have this polynomial dependence of the stiffness matrix on decision variables, because this can be reparameterized as a polynomial. And we will return to the most basic setting of minimum compliance design. So we have, just to make things a bit more interesting, some design-dependent loads. We are minimizing the compliance, but this compliance comes from NC load cases, which are distinguished by this particle symbol here. And these load cases are assigned with some pre-selected weights, denoted here as E. Each load case must verify this system of linear equation when this K is polynomial function of A. We have the resource constraint, which tells us that the number of volume, the volume we can distribute among individual elements is bounded from above by some resource constraint. And as before, there is non-negativity assumption on cross-section area. So again, everything is reparameterized in terms of cross-section areas, but now the dependence is polynomial and it's non-linear. So actually, repeating in verbatim the arguments from part 1, this can be rewritten as polynomial matrix inequality. So we have the linear term here with a new variable. We have the semi-definite constraint here and two linear ones. And because these polynomial matrix inequalities are non-linear, this gives rise to non-convex form. So yeah.
So if I understand correctly, in the first part, the matrix K and the IE constant?
0 even. So well, technically it works exactly in this way. So I mean, by some, so if you think, for instance, about Eiffel Tower. So if you take this individual bits from which the structure is built, if you connect it via some pin type of connection, actually it will never bend. It will only extend and contract. So for that reason, by some structural arrangements, you can eliminate this bending effects. So part 1 was actually working only with this red part of the stiffness and mass matrix. And the reason was that it was linear and we were able to solve it with linear semi-definite.
The second part, the IE is second order polynomial in.
No, it's some polynomial. Second order is the most simple case, but you can parameterize your cross-section by different quantities than cross-section area, but it will be just polynomial dependence. But in the most simple setting is just second order polynomial. Okay, so this is it. This is our polynomial matrix inequality problem we would like to solve, because this is linear, hence polynomial. So we will approach it using standard machinery of the Lasser hierarchy. So again, I really feel inappropriate to repeat the story here, which we actually heard during the lecture yesterday. So this is the non-convex problem we are trying to optimize, to solve. We can formulate it as infinite dimensional convex reformulation by X-parameterized linear constraints, or by minimizing over the cone of positive polynomials on the domain over which the structure is defined, as I try to support by this naive sketch. And we know that this can be relaxed using probability measures and reformulated as an infinite dimensional generalized problem with moments. By results by Guillen and Jacques Lasser, well, there is an assumption that generalizes this standard Archimedean assumption to matrices, if I got the message correctly, which says that if we are able to find two sum of square polynomials specified here, such that the superlevel set is compact, which because we are working with polynomials means actually bounded, then this form can be approximated by a finite dimensional truncation sequence, when R here denotes this relaxation order, Y are moments of our variables, which are subjected to the standard constraints. So this just has that, you know, it's probability measure, if I got the message correctly. And these are two matrices. One is related to moments, and second one is so-called localized matrix. And for the computation, it's convenient that these are linear semi-definite programs we can solve. So this is what is attractive computationally. What I also like is that there is well-developed theory behind that. So by this relaxation property, obviously, each relaxation produces a rigorous lower bound on our objective. The convergence is monotone. There are rank-based sufficient conditions of global optimality and algorithmic procedures how to extract all globally optimal solutions. So again, you know that much better than I do. So this is what we have at our disposal. And the question is now how to apply it to our problem. So, yeah, sure.
Question. So can you describe more precisely the constraint with a G here? Because you have G of X times 1, so this is what?
Yeah, so sorry, I was kind of, yeah, so
the matrix.
Yeah, so this is something which in this particular paper is called localizing matrix. And there is a procedure how to determine that. Perhaps there are people who can explain it more, but well, this is the standard Lasser type of notation.
Yes. Can you hear me? It's Didier Rian.
Yeah, sorry. So what?
Yeah, no, it's just a kind of a matrix form of localizing matrix in the sense that capital G is a matrix, so it's just a tensor product with the elements of G. So it's constructed in the same way as it is done with scalar constraints, but here we have symmetric matrix constraints. So it's just tensorized localizing matrix, nothing else.
Yeah, thanks for bringing the explanation.
So if you want to know exactly how it is computed, then you can get to the paper, but it's nothing really sophisticated. It's rather straightforward.
Kronecker product.
Yeah.
Yes, absolutely. Kronecker product. Yeah. Yes, Bernard.
Yeah. So yeah. Thank you, Didier, once more. Okay, so this is how our problem looks like. Well, you like to solve. The problem is that the assumption on which the whole theory is built is not satisfied, because if you take arbitrary non-negative cross-section area, if you take compliance is large enough, so the C, we can see that actually this constraint will be satisfied, so this is not bounded. So as usual, we need to add some well-founded bounds to the problem to make it solvable, which have theoretical advantage, but also help a lot computationally. So there is obvious upper bound on the cross-section area. So this corresponds to the case when we take the available volume and assign it to single element. There is also very natural upper bound on the compliance, which is actually based on something we call uniform design, meaning that you take the volume and you distribute it uniformly among individual elements in the structure, and you just compute the compliance by solving the system of linear equations. So this is again very cheap. So with these bounds, then we rescale or scale the design variables to -1, 1 by standard linear transformation, and we also add this bound, this constraint in this particular format, which eventually, allows us to reformulate the problem in this dimensionless or rescale form, which satisfy the basic assumptions. So then this problem is treatable by standard machinery of movement of squares hierarchy. So we have what we wanted to have. However, being primarily educated in mechanics, we were also to refine the results a bit, mainly concentrating on first order movements of these two variables with which we optimize, so this cross-section areas and compliances, which follow from our relaxation. So actually you can take this first order movements and you can map them to, well, cross-section areas which are scaled back to the physical domain, so to say, or the original domain. And you can take these values and compute the compliance of that by solving the system of linear equation. And actually, Mark was able to show that these two solutions are admissible, and hence, by some minimality property of all mechanics problems, they simultaneously provide an upper bound to your solution. So what we have now at our disposal is this value of the objective function we got from this reconstructed solution. We get the lower bound which follows from Lasserre hierarchy. So now our sufficient condition of global optimality is just simply taken by subtracting the lower and upper bound and requiring it to be below certain threshold. So, and we are also able to prove that if we have problems where the global minimizers form a convex set, we have convergence. So, I mean, as I will show in the example, this is, not so strong condition as rank condition standardly used in this hierarchy, but its major advantage is that this is very easy to test, and we immediately get the quantities of interest as the first of the unit. Okay, so this is the slight bit we can add to existing theory. So now to examples. So what I would like to show first is this example, which consists of two bars connected in this point. Well, this scheme means that this is fixed, it cannot move. And this is how the cross-section area or cross-section of the particle example looks like. So, I mean, in this field, this is some kind of whole world type of problem. Despite that, actually, it has three distinct local minima in decision variables, which are visible here. And if you just apply the machinery, it converges in second relaxation to the global minimum, which is certified. And it converges also according to our mechanist kind of criteria. So if we play with that example even more, adjust the parameters a bit, it is not so difficult to actually make the example in the case when there are two distinct global minima. And what we can see in this particular case that according to our criterion, actually it does not converge because the set of global minimizers is not convex, it's composed of two separate points. But according to the standard rank condition, we were able to detect that we converged. So this just shows that there is some intrinsic limitation of what we propose. And finally, something which is a bit closer to application. So this is the ground structure we are considering. This is the particle parameterization of cross-section, for which again, everything can be parameterized based on the thickness, for instance, of base graph. And we also benchmarked our approach against local optimization solvers, namely with PanLab when we started with this nonlinear matrix inequality and then standard MATLAB optimization toolbox, and some techniques which are available in structural optimization literature. And this is kind of shows some sampling of solution you can obtain. So the worst one in terms of performance is something we obtain after the first relaxation. We have convergence after second relaxation according to our criterion. So we know that this is also a unique solution, by the way. And you can see the range in which we are located. And then according to initial starting point setting of the parameters, the local solutions, they converge to different configurations. Of course, this is not to criticize any of these. They are local, so they do exactly what they say. So for this case, for instance, we are able really to obtain a certified global minimum. Okay, so this pretty much brings me to conclusion of part 2. So I hope that I was able to convince you that we successfully extended trust topology optimization to beam optimization by relying on Lasser relaxation hierarchy. So this is yet another application of this very interesting and general concept. We added some simple sufficient condition of global epsilon optimality with standard convergence result. Of course, there are some limitations. Currently, this is limited to small scale benchmarks, although Marek does not like when I make things like that. So there are some cases when this can be adopted in which you have a handful of optimization variables. What I have not shown is that this also extends to shell structures, the one which I talked a lot in part 1. And in all cases, we actually obtain very rapid convergence of the hierarchy. And again, I would like to thank the funding agency for supporting this research. And again, if you are interested in more details, there's archive preprint or published version of the journal, which is focused in a structural and multidisciplinary optimization. Oh, so in remaining 1 minute I have, well, I will briefly speak about possible extensions. Well, actually, there hopefully, and in my interest, there will be some extensions because we were lucky enough to get additional funding for a follow-up project in which we promised to extend the study case to dynamics, so to time-dependent problems, and also to increase the size of the problems which are tractable. Here, our preliminary thoughts are on exploiting sparsity, because I do not know whether you recall that some part of the lecture I mentioned that the matrices are sparse, but we have actually never used it. So we think that there is some potential for that. Well, the team is, well, I'm really happy about the team because it integrates 3 groups. One is positioned as Faculty of Electrical Engineering, and it's led by Didier and Rion and Jakub Marecek. The team positions partly, and Czech Academy of Sciences is formed by Michal Kočvara, Jiří Outrata, and Marek Tiburec. And well, this is the civil engineering part. And the reason why I'm so speaking about that for so long, that we have 2 openings available. So there is a PhD position which has already been announced at Faculty of Electrical Engineering, and there will be a postdoctoral opening in approximately half of 2022. So if you are interested, or if you know about someone interested, well, I think this is a nice opportunity to spend some time in Prague, to work with some brilliant researchers and also with me. And well, so please spread the word. So with this, I would like very much to conclude my talk, to thank the organizers once more for the invitation, and most importantly to the audience for their patience when listening to my talk. So thank you very much.
Many thanks, Jan, for the very interesting talk. So we are supposed to end now, but I guess we can take some time for questions. So if possible, I would like to ask 2 questions.
Yes, I'm all ears.
So the first question is about running times. So if you go to slide 44, you compared the different techniques. So I guess nonlinear SDP solvers with your hierarchy of LMIs. So
yeah, so it's incomparable, as you may imagine. Precise times are in the paper, and it's by order of magnitude more. But my viewpoint is that it pays off to make for certified globally optimized solutions. So, of course, I do not know how this is popular in industry, but this is my viewpoint. So, of course, this is much more involved.
Oh, really? Okay. So for instance, is it slower than PenLab?
Yeah, but well, as you increase the relaxation order, of course, it explodes. So, I mean, the size of the problem you are solving is so much larger that even the linear SDP solver is unable to beat the candidates. But we are not really well here. Really, I think that there is sufficient room for exploiting sparsity, which is there by definition of by mechanical principles in which the models are built.
So it was my second question. So about this sparsity exploitation. So I don't know if you are aware of that. There is a paper by Fantuzzi and Zhang that handles sparse PMIs. So sparse in the sense that the matrices have so the matrices with polynomial entries, they have a lot of zeros.
Yeah, sure. So well, this is to be hopefully explored within the follow-up project. And again, I'm really glad that I was invited here because, well, this is the place when these developments are made. So I do appreciate that. So
one of the tricky questions is whether you will be able to extract the minimizers.
Yeah, sure. So I mean, but my hope is that with this first moment type of interpretation, we are on the good track. But of course, well, ask me next year once we will be working on this topic for a while. I cannot say no. But thankful for this comment. I appreciate it.
Okay, thank you. So I don't see any questions in the chat. Any questions in the audience, remotely or physically?
Maybe I have one. Yeah, maybe if you go to the same slide we have seen before with that last example, right, where you compare all the solvers.
Yeah.
So we can see here that the optimality criteria method, I guess this is what OC means, right?
Yeah, precisely.
Sorry, by chance it finds the global minimizer, right?
Yeah, this is complete coincidence. So, I mean, with the default starting point, which is this uniform design, meaning that you take the available volume and you distribute it uniformly within. So in this particular case, it converged to the optimal solution. But this is, of course, coincidence.
Yeah, but my question has a second part, so I guess this I already know this, but the question would be, I mean, these people propagating optimality criteria methods and stuff like this, they would always say, if you go for compliance minimization, there are only very rare examples because compliance is very forgiving for which you would sort of find a bad local minimum. And then these optimality criteria, you eliminate the state equation, what you probably did, right? And then it's very fast. And you probably solve that in a fraction of seconds.
Yeah.
But that's why my question, sorry, I'm coming to the end now. My question is, do you have more of these interesting examples where it's clearly known and seen that you have actually different kind of local minima, which could be used as a benchmark to prove that this is just by coincidence that they find that the global minima is? Because it's not, I think it's definitely not true in general, right? What they say.
Sure. So yeah, unlike most people working on topology optimization, I share your opinion. And thank you for this proposal. So this is what we did. I do not know whether Mark is connected or not, but he can certainly, try that after defending his thesis. That's a good option. I mean, the methodology is here. So now it takes some patience to find out particle examples in which there is a difference. So thank you for proposing that.
But that's already very nice for me.
So heavily dependent on initial gas. So I mean, if you started with close to, for instance, this solution, no matter what these my colleagues say, I think inevitably it will converge to this one. So we can certainly explore it too.
Okay.
Thank you.
Thank you. Thank you. Very good talk.
Okay, maybe a last question.
So you had the results where the upper bound from the extracted approximate solutions converge to the lower bound from the hierarchy.
Yeah.
If the set of global minimizers is convex. I suppose that's a general property for the last level hierarchy. It's not something specific for your
Thank you.
problem.
Yeah, thanks.
But that's my guess. I think it would be probable that this is the case.
Okay. Yeah.
The first order moments will convert to moments of a metal convex power.
Yeah. Yeah, so this is what we use.
I would expect that.
Yeah, correct. I think this is exactly the argument we use, but I overlooked the stuff of general. Yeah, this was our argument.
Okay. Yes, please, Michel.
Just one last question, sorry. About the sparsity, because as looking at this example, the stiffness matrix is dense. So is there really sparsity for this particular example?
Correct. Yeah, so we will certainly need larger examples to exploit sparsity. That is correct. Sorry, that was overstated.
Okay.
Yeah, you are right. I was talking faster than I'm thinking. Using my thank you. Yeah, that's good.
Okay. If there is no more question, I would like to thank you, Jan, again for this very nice talk.
My pleasure.
And we resume at 3:30 with Lorenzo Baldi.